So we have seen quite a lot of various topics, and we have basically an overall good pictures of what is the dynamic of our universe. So we constructed our relativistic covariant theory of gravity that we then exploited to construct our universe in the sense of the description of the background. So how the universe as a whole is expanding or contracting as a function of time. And by solving the Einstein field equations, we basically arrived at the Friedmann equations that gave us this relationship. So how A evolves as a function of time given a certain curvature and given certain ingredients in our universe: dark energy, dark matter, baryons, and radiation. Okay, so these are the main ingredients that you consider so far, on top of which we had to include the inflaton field. So another scalar field that is acting at early times, so at the very beginning of our cosmological history. And this field provided this accelerated expansion that explained and fixed all the issues that were left in our standard model. Okay? Moreover, we also studied the reheating process that, if you want, is the first thermal process that we encountered in this journey, in which we saw that the inflaton field, by spontaneously decaying, okay, gave rise to the particles. So its energy got transferred into the production of particles. So therefore, inflation naturally ended. Plus, we had now particles to play with, the one that we're going to discuss now. All right, so that's the history so far. Now that we have our framework, we know what the universe is doing as a dynamical object, we are in the position to study what happens inside the universe. And therefore, we are going to study what happens to the particles and to the fluids that are constituting and filling up our universe. And therefore, we are going to start the journey, not in terms of dynamic of how the expansion of the universe goes, because this you already know, but we are going to look, given this expansion, what happens along the way, different stages, to the main actors that are going to be the baryons, radiation, and dark matter particles. Okay? Dark energy, we already discussed everything about it, so we already know the dynamics and what it's going to do as an interplay with the expansion function of the universe. So now we are going to focus on the particles. Let's start to give an overview of what we are going to encounter, so that you know what are going to be the various stages of the process and the various equations that are going to describe all these different stages. So we start by time 0, okay, where there is this black line here is the region where our theory completely fails, because we are basing our theory on gravity, and gravity doesn't work at those energy scales. Okay? Therefore, what happens here, we don't know. We don't have a quantitative answer, all right? Then we have this vacuum, so we have this field at the ground level, that then in various regions, so there are these quantum fluctuations that we have seen. In some regions, the field might reach those initial conditions that give rise to an inflaton region, an inflation region, okay? Here, one of those regions start to inflate, we have inflation, and this represents our universe. Then we have reheating. So here we have this release in energy. So we have this crazy expansion of the universe, temperature drops, but then the energy of the inflaton field gets released into the particles, the temperature rises again, right? So that's the hot Big Bang. That's where we start. We start with a plasma, which has extremely high temperatures. That's the trick. And that's the key to understand all what is going to follow. Because then, as you know, the universe is going to expand. Here, we are in radiation dominations, as we've seen. And the temperatures start to drop. It's starting to go down with the power of 8 to the power of -4, right? Don't fade. So the temperature is going down. And since there is an evolution in temperature, the energy scales that we are encountering along the way are going to change, because the temperature is changing. And with that, the particles, various different particles, are going to interact with each other or not, according to the temperature that we encounter along the path. Therefore, in different stages, there are going to be different interactions between particles, and that depends on the temperature that evolves as a function of time. That's the key idea. Then what we have? We have a period here which is kind of, we don't really know what's going on, therefore I'm not going to spend much time about that, because from the particles that have been created, or fields that then give a particle, the situation can be more complicated than what I said here. Depends on how one constructs the model. I told you several times that the description there is very model dependent. Nevertheless, at a certain point, baryons must pop up. Why? Well, because we see baryons, right? Therefore, we have the formation of hadrons, we have the formation of baryons, and so on at the very early stages after inflation. After this period, the temperature continues to go down, and we have the first decoupling. So here, all reactions are extremely efficient, and we have a perfect equilibrium between the different species. But we have seen already that these sort of interactions might not be sufficient to maintain equilibrium. That's because the universe is dynamical, is expanding. It's not like this room, which is closed volume, and then, you know, it thermalizes, the temperature is equal all over the places, if we consider it as a closed box. And we forget also about gravity to avoid gradients in buoyance due to and buoyance that is due to different in temperature. So avoiding gravity, this would become completely homogeneous in terms of temperatures. Thermalization. If we expand our box, the temperature drops and we can go out of equilibrium if the expansion is faster than the reaction time. We have seen that, right? This was this very simple criteria in which we have the expansion rate and the reaction rate of the particles. Whenever the reaction rate is much larger than the expansion rate, meaning the reactions blah, 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 are super fast with respect to the expansion, then the reactions are efficient. If instead we reach this condition, it means that the box is expanding fast enough, our universe is expanding fast enough, and the reaction rate is decreasing because the particles are sort of finding hard to meet each other, okay, on average statistically, and the reaction drops. These would be the conditions for freeze out, okay? That's called freeze out. And in this process, I gave you just this simple criteria, which is sufficient to understand if a reaction continues or not. But I'm going to give you another equation, which is the Boltzmann equation. Which fully characterize how the reaction is proceeding. Okay, so it's a quantitative prescription of how a reaction is proceeding as a function of time. And the reactions that we are going to consider are always two particle-particle interaction. Like this one. For example, positron and electron annihilation, two photons, for example. Electron scattering, photon and electron, photon and electron. That's a scattering process, and so on and so forth. Among the various processes, we are going to consider, for example, the formation of deuterium, in which we are going to have protons, we are going to have a neutron, and they are going to merge to perform deuterium and photon. Okay, so you see always two body interactions. Why not three body interactions? Why not three particles on this side that are going to give a product on the other side? Because they are rare. Imagine you have three particles of the right species to produce this species, this reaction, if we would have another particle here, so three bodies, that have to meet exactly at the same time. How likely is this? It can happen. The universe is vast, so this can happen, but it's very rare. So we just forget about it. It's negligible, and we can just forget about it. That's why we will always consider two-body interactions of this sort. All right? What else? Yeah, just going to this reaction with this criteria, also that we used during Gesundheit, during the reheating process of, we basically add equilibrium, two arrows. The reaction rate is, for example, the reaction rate is efficient. We have this inequality. Or whenever we hit this condition, then the reaction stops. The Boltzmann equation describes all these processes in a continuous way, considering all species. Okay, so it's not like on-off. There is a transition, and this equation is going to tell us. So this is going to be the key ingredient of our discussion. All right. So let's give a look at the, now that we know the context, we know what's going to happen, let's see the various processes that we are going to consider. So I already introduced baryogenesis, then let's skip the phase transitions. We might have, in this epoch here, dark matter freeze out, in which you might have the dark matter particles reacting. At that part of the stage of the universe, density was relatively high, and the density is high, and therefore reactions are likely. Moreover, velocities are high because temperatures are very high, so this helps the reaction to burn. But at a certain point, as the universe is expanding, we might hit, for that kind of particle, this condition, freeze out. The number of particles of dark matter remains constant within a co-moving volume, meaning there is not anymore creation or destruction of particles. And creation and destruction of particles you see from this expression. Because if the expression, if we have this condition, these guys are destroyed in favor of these ones, of the products. If the reaction goes the way around, then these guys are destroyed in favor of this one. So you have creation and destruction. So actually it's like destruction of this guy or creation of these guys in favor of the various species. If you have the equilibrium, as many are destroyed as are created on both sides. Okay? So whenever this reaction stops, then we have the freeze out, and the number of particles that once was participating to the reaction is constant. The number is fixed, meaning the number density in co-moving volumes is constant. Okay? No creation or destruction of particles. This would be the freeze out of dark matter that happens somewhere here. We don't know. Then we have the neutrino decoupling, because we have neutrinos that are neutral particles, right? And therefore, they're not going to interact through the charge because they are neutral, but they're going to interact, for example, with electrons with the through weak coupling, right? There is the weak force, both guys feel the weak force, and they can interact, therefore, one with each other. At a certain point, the freeze out is going to happen, and the neutrinos are going to be decoupled from the electrons. Freeze out, their number density is constant. What is that? That's a background of neutrinos. These are cosmological neutrinos that have been produced by the reaction produced across the universe. So these are not like the solar neutrinos that are produced by nuclear fusion within the sun. These are reactions that occur across the entire universe, and they're called cosmological neutrinos. At the freeze out, they do not participate anymore with the reactions, and they stay like that. I'm a neutrino, I do my neutrino life, okay? Which is very solitary because you know they interact very little with any other particle. And this constitutes a background. So right in this moment, we are basically crossed by gazillions of cosmological neutrinos. And the temperature of those neutrinos is predicted by the equations that we are going to compute. Okay? Why I say predicted? Because at the moment we don't have, well, because we can do the prediction, and we cannot do a measure. Because their density, their energy is very low, because we are talking about energies for these neutrinos on the level 1.9 Kelvin, so very low temperatures, very low energies, very difficult to detect. We don't have detections, but they are predicted. At a certain point, if we are going to have good instruments and maybe some better idea to build up instruments, we could detect this neutrino background, and with this detection, we could probe these energy ranges to verify if the model that we constructed is actually holding up, right? Then the universe continues to expand, the temperature starts to drop down. Right after, there is a process which is called electron-positron annihilation. That's the reaction. Let me put it a little bit higher. This is the reaction, I've lost it here, where we have the annihilation of a positron and an electron giving photons. What happens at this point? Whenever we have equilibrium, the energy momentum that goes here is also going back. But at a certain point, we have a freeze out because the energy that is contained by this photon, remember that we have redshift, so it's they're redshifting, the temperature is going down. The energy of these photons is not enough to produce the energy, mc squared, times 2, because we have 2 particles, on this side. And the reaction stops. Okay? Energy momentum conservation, remember? The energy that to produce these guys, you need an amount of energy here which is sufficient at least for their rest energy, mc squared for each particle. When the sum of these photons is below this threshold, the reaction stops. Okay? What happens? That when this reaction is active, we have a incoming energy from the electrons to the photons once the equilibrium is broken. And we have a net energy transfer between the electrons to the photons. The photons get higher, get a higher temperature. Okay? So imagine a thermal plasma in the beginning, everything is in equilibrium, all particles have the same temperature, photons and neutrinos. At a certain point, this process starts to be active, energy, the electrons start to annihilate and give energy to the photons. The temperature of the photons starts to go up. Are the neutrinos following? No, because they're already decoupled. They don't care about anybody anymore. And their temperature is their temperature. Therefore, the energy that is going, the energy that is released to the electrons, the photons, remains in the photons. The neutrinos have the temperature. Therefore, we have a neutrino background with a temperature nowadays of 1.9 Kelvin, and a background of photons, these guys, that have a temperature of 2.7 Kelvin, which is higher. And the difference in temperature is given by this event, the electron-positron annihilation, followed by little the neutron decoupling. Temperatures continue to go down, and what happens? We have neutrons and protons, we have a pot of them that are not heavy elements. Okay, where is the helium? There is not, it doesn't exist. But the temperature at this point are so low that neutron and proton can bind together. Okay, we don't have any more photons with an extremely high energy that would photodissociate it immediately. Before, if they meet, I found you, then arrives an even photon with high energy, boom, and photodissociate our newly formed, for example, deuterium. Okay? We are going to see that to arrive from protons and neutron, this pot, to produce helium, we need a chain of reactions that involves first the production of deuterium, which is nothing but an isotope of hydrogen. Deuterium is just 1 proton and 1 neutron. That's still hydrogen, because that's the type of the atom is given by the nuclei, by the nucleus, by the charged particle in the nucleus, meaning the protons, 1, but is an isotope with 1 neutron inside. That's deuterium. Then with this guy, some other reactions can follow. There is a chain that we are going to follow, different reactions that are talking well with each other, and we are going to have the production of helium, lithium, and a little bit of beryllium. Most of it is going to end up in helium and hydrogen. Okay? These are really traces. And with this sort of equations, we are going to have a prediction for how much helium we expect to have. And guess what? If you take the telescopes and you search in regions in the space that have not been polluted by production of heavier elements by stars, for example, because the stars are producing heavier elements and they are polluting the universe. If you search for regions in the sky far from stars and far from processes that might have created additional heavier elements, then you might measure the original amount of helium, so the balance between hydrogen, helium, and the rest, but basically these two guys here, and compare it with your prediction coming from the baryonic, from the BBN, from the cosmological nucleosynthesis that is happening at this time. And guess what? Yeah, it works. The model is working. Okay? How much time in humans' clock passed from that moment, so the Planck epoch, to the baryonic nucleosynthesis, so to the cosmological nucleosynthesis, the BBN? 3 minutes. 3 minutes. So all of that happened in 3 minutes, and we have the formation of the first heavier elements. Okay? The rest of the periodic table, silicium, oxygen, iron, and whatever, didn't exist. All of that stuff got created by stars, okay? That then start to get formed much later on in this region here. But before arriving at the creation of stars, here we have this phase in which the universe is like the interior of a star. All over the place is like the interior of a star, because this is exactly the process that is taking place within the sun, okay? It's one of the chains that are within the sun. Then you continue to cool down, that's fantastic, life move on, and at a certain point, we have another event of freeze out. We have the photons and the electrons that are now not going to talk one with each other anymore. That's because the free electrons disappear. The universe becomes neutral, okay? Becomes, well, it's still neutral, but what happens is that we had, from a plasma, we start to have the production, where are we? Recombination, here. We have this process that is taking place. The temperature is low enough such that the electron can combine with protons. We have an hydrogen atom. Before we had only nuclei, okay, fully ionized. Here we have a neutral hydrogen, not ionized. Beautiful. We have our beautiful core of the atom with its electron. Okay? So what happens when this happens, when this occurs? There are not anymore, I mean, there are few, but most of the free electrons are gone. And the photons are not scattering with those free electrons anymore. They're free to travel. Okay? Therefore, we had the electrons are gone, the photons that first was scattering with the electrons are not scattering anymore, and they're free to travel. That's the moment in which the radiation, so the photons, are free, and it marks the origin of the cosmic microwave background. Like for the neutrinos that got free at a certain point, here the photons get free, and they're allowed to travel across the universe and reach us. Okay? That's the cosmic microwave background. And of course, we're going to study this process as well. Then, something else happens here. Afterward, after the universe got filled up by neutral elements, you have neutral hydrogen and helium and so on, that the universe get reionized. This is, well, get ionized. Okay, that's an epoch in which the universe receives high energy photons that photodissociate the hydrogen that is across the universe. How it happens? The temperature is still going down. Where are these photons coming from? Stars. Okay? We have the formation of structures. Therefore, at a certain point, we have the matter start to condense, create galaxies. Within galaxies, the temperature and the pressure and the densities are sufficient to create stars. The stars, especially the very massive one, when they get born, they emit a lot of hot radiation in the ultraviolet. And these radiations has the frequency and an energy which is high enough to photodissociate our neutral hydrogen. Our hydrogen with the proton and the electron gets scattered out. The universe gets reionized. Is again completely, is like a plasma again. And the process is due to the stars, okay? This is happening here. And the study, this astrophysical process is extremely important because how it happens affects the properties of the cosmic microwave background, okay? As we observe it. Because this radiation, of course, is traveling free, but if now there are again free electrons, they can interact again. And what we see for those, of those photons, it depends on how they have been produced, the cosmic microwave background, but also what happens along the way, reionization, for example. So we need to understand this astrophysical process to better understand the cosmic microwave background and all the cosmology that is linked to it. Right. And this basically ends our journey across the thermal history of our universe. Okay? So we will arrive up to this point, to the reionization of our universe. All right. Afterward, we will study the formation of structure, but that's the story of thermal history. All clear? I throw at you a lot of information. Yes?
What happens to the Big Bang nuclear synthesis and recombination? Because it's or the measure radiation equality, like what happens?
Nothing really. I mean, equality is just it just marks the equality between the density of matter and radiation.
What happens with equality? Like all the time, like we still have the process before, like the creation of helium and everything, or what happens?
Yeah. All of this is radiation dominated. So up to where is nucleosynthesis, reionization. So we are recombination, photodecoupling. Up to here, we are still in the radiation domination epoch. Okay, so photons are the king in, they are the thermal reservoir, if you want, for the particles that interact with them. Those that don't interact, they are not represent a reservoir, so the temperature is not shared because there is no interaction. Plus, all the relativistic species are the one that determines the expansion of the universe. So so the equality time is the time in which one species or the other are going to rule, okay? So this affects the expansion of the universe. But the thermal processes that we're going to consider are all in radiation domination. Yeah?
Just a more technical question. Do we consider the inflation time also to be radiation dominated, or do you
No.
also talk about that you could identify it with dark energy?
So the epoch of inflation is not radiation domination, because what is leading the expansion is what? The inflaton fields, and that's not radiation, right? Then when the inflatons start to, there is this roll-over phase, so it behaves like the cosmological constant, almost. And after the slow roll phase ends, the fields start to oscillate. So it behaves as matter. So the universe expands as matter domination. Then we have the reheating process, in which we have an energy release, very strong, from the inflaton field to the creation of ultra-relativistic particles. And all ultra-relativistic particles, they behave as radiation in terms of the expansion of the universe. So we have expansion, so we have basically the inflationary epoch, which is dark energy-like, okay, or if you want, lambda-like. We have a matter phase where the inflaton starts to oscillate. Then we have the reheating, when we have the production of ultra-relativistic particles, and from this moment on is radiation dominated. Radiation dominated up to the equality time, which is, it's roughly here, okay? And here then we have the formation of structure. Here from now on, we start to be matter dominated with the contribution of the cosmological constant, or if you want, the contribution of dark energy. So nowadays, there is not one species that is dominating. We have two that are delivering the expansion of the universe. Okay. Yeah? Sorry, again?
If I want to reread this in a textbook, like where could I find that?
The plot? Oh.
Also the information below.
Oh, I didn't mark the, I mean, I modified by adding few labels, and I forgot to save the reference, so I cannot tell you. Okay. So at the moment, you find it in the script. All right. Good. So that's the story, the thermal history of our universe. That's what we're going to do in practice. So first of all, since we are dealing with ultra-relativistic particles, we need, first of all, a small recap about quantum gases. Therefore, we need to understand what are the properties of quantum gases. For example, how they behave in terms of temperature, pressure, entropy, and all of that as a function of temperature. Okay? Then we are going to study in a bit more details the condition for thermal equilibrium. Afterward, I'm going to give you the Boltzmann equation that tells you, given this ratio, what is going to be the production or destruction of a certain kind of particle. So with this equation, we will study the evolution of the number of particles of a certain kind interacting or not with other particles. Then we will encounter the neutrino decoupling, which is a very simple process where we have this reaction that is going to be truncated, as I mentioned. We have the photon reheating that I already explained, in which we have the annihilation of positons and electrons giving photons, therefore rising the temperature of photons with respect to the one of the neutrinos. Before, when the reaction was efficient, the two were coupled and the temperature were the same. We have decoupling, this stops, and the two temperatures can evolve independently. We have reheating, the reheating of radiation, and we get a kick in the temperature in the photons coming from the annihilation process, right? Then we are going to study cosmological nucleosynthesis. We have the formation of the elements and recombination and the photon decoupling that is giving rise to the formation of the cosmic microwave background. With that, we are going to exploit the Boltzmann equation, use few approximations, and derive the SA equation, which is the equation that tells you how this process is taking place in detail, okay? Because otherwise, the Boltzmann equation in general is not solvable analytically. So you need to do some approximation to get the solution. This would be the natural evolution of the universe, but what I will do is I'm going to flip these two, okay? Why? Because this one is just this interaction. It's simple, and we have only one SA equation describing this process. For the baryonic, for the cosmological nucleosynthesis, we have a series of reactions. We have several of them, and they're going to talk one with each other. Therefore, before encountering this complication, I'm going to study first a simpler case. So I'm going to follow the evolution of the universe up to here. We will jump to the recombination of photons, of electrons, therefore to the CMB. And then, pop, we are going back to the cosmological nucleosynthesis because it's a bit more complicated. All right? That's what we are going to do. All right. Now, this is done. And we can have a little break. So I would say 10 minutes, since I started late. So we can meet at 10 past. And we will start with